So I'm going to speak about joint work with Elio Marconi in Padova now about the eikonal equation in 2D. So very simple equation. I'm going to start by writing it down. So I have a domain in 2D. We are looking at vector field on the domain, which have zero divergence and unit normal. Okay, so maybe this is not what you know as the eikonal equation. More classical to think of this equation, normal gradient u equals 1. Since you are in 2 dimensions, the fact that M has zero divergence is equivalent, at least locally, to it being the gradient of some function rotated by pi over 2. And so this becomes your classical, maybe more classical eikonal equation. So this is the hyperbolic equation, which is maybe not that common when you do calculus of variation. In particular, with respect to elliptic equation, the new thing is that you don't expect to be looking at smooth solutions, right? Because if you have smooth solutions, they're constant along characteristics, and so at the end they cannot be smooth, usually. So in general, people look at weak solutions, but then the issue you have with weak solutions is you have too many of them. They're just too flexible. So let me just give a few examples of weak solutions. I give 2 examples that you have maybe something to think about. One example is just some kind of vortex here, just singularity in the middle. And another type of example is just a jump between 2 constant values. And if the normal component of the jump is continuous across the jump, then it's divergence free. Okay, why not? So in general, I mean, weak solution of the eikonal equation, if you want a good notion to have restore some uniqueness of the boundary value problems, people look at viscosity solutions, which are the ones you obtain when you add an elliptic perturbation to it and it tends to 0. But here I'm not interested in viscosity solutions. Instead, in what have been called entropy solutions, then let me tell you what they are. Maybe I should have done like my domain divided into 3. So entropy solutions. Entropy solutions are those solutions of these equations, in principle here this is just very big, which satisfy the additional constraint that if you take the divergence of some nonlinear functions of M, it stays not 0, it stays measure, and this should be true for all nonlinear fields that we call entropies. Let me tell you what they are. Entropies, so they are smooth vector fields on R2. Actually, you just need to define them in the unit circle because this is where your solution M takes values, right? Smooth, yeah, smooth can mean, for instance, C2. Which, okay, I'm gonna write down a formula that is not very illuminating, but this is the definition you can take. So you look at the derivative of P with respect to the angle in S1, and you want it to be tangential to S1, perpendicular to the normal. Okay, why not? But I mean, the important thing is that this condition is really equivalent that if you take M a smooth solution of that, and P that satisfies that, then this should be 0. Okay, so now it makes a little bit more sense to look at these things, because basically, if you have a smooth solution, these objects, which are really just some distribution, are going to be 0. So what you expect is that those are objects that detect the singularities of your solution. And here I'm putting some constraint on the singularities. I want that these objects, which are distributions of order -1 in principle, are actually of order 0. They are measures. All right, so I mean, you could say, why are we interested in this class of solution, which is nicer than just any weak solution, but is still quite large. This comes from the Aviles-Giga energy, as Luke said when he introduced me. And okay, I will talk, and I don't have that much time. I'm not gonna write down the energy, but just this is why we're interested in those solutions. This is because they come from a variational problem. And in fact, in the sequel, I mean, you're not gonna need to know what the Aviles-Giga energy is. Just know that this is why we're interested in that. Okay, and for that issue of understanding important things about the Aviles-Giga energy, the main question is concentration properties of those objects. What we would really like to know is if those measures, they are supported on the 1D set that we think of as the jump set. Okay, so why would you expect something like that? Well, for instance, it is true if M has the additional regularity property that it has bounded variation. If M has bounded variation, you have a chain rule, and because of this property, when you apply the chain rule, all the thing that is related to the diffuse part of the derivative of M, it just goes away. So you're just left with the jump part, and you end up with an object that is one-dimensional. Okay, but the bad news, or good news if you want to have something to do, is that in that class of solutions, there are many solutions that are not BV. In fact, you can characterize it in terms of Bezoff regularity of order 1/3, so it's really far away from BV. But still, we cannot expect that they share many properties with BV maps, these entropy solutions. And the first result in that direction was by Lellis and Otto, 2003, where they proved some type of BV-like structure of entropy solutions, which I'm going to explain now. So there are basically 2 points in the result. The first one is a description of a more precise description of that measure. Okay, so let's imagine for a minute that M is BV, then I apply the chain rule, and what I get on the subset is the difference between I on one side, at the value of M on one side, the value of M on the other side, dotted with the normal vector to the jump set, and this is the 1D part. Okay. And in their result, you have something else here that you would like to be 0, but you don't know that it is 0. So here, that something else is just some measure that is orthogonal to H1. So any set of positive H1 measure has 0 new measure, right? And here my JM, it's like it would be for a BV map. So it is the one rectifiable set. It has traces on both sides, etc. So that you can make sense of this formula. So basically, that first point is that they show that the one-dimensional part of that measure really is exactly like one of a BV map. But they cannot rule out that there will be a higher dimensional part.
Mu is a kind of counterpart in the decomposition of the gradient in BV.
Yeah, somehow you can think of it like that. Except if M were BV, the counterpart, you would just not see it when you compute this, because you have the chain rule, and this would just be 0 because it's 0 when you do.
Yeah, but I mean, this kills the absolutely continuous part with respect to the Lebesgue measure.
Yeah, this kills also the counterpart.
Also the counterpart.
Yeah. So really, if M is GV, then just mu is 0 and there is nothing left to do. And the second point, which is the one we are going to be more interested in today, because we cannot do much about that thing yet, is that if you take a point outside your jump set, then it has vanishing mean oscillation. Let me just write down what I mean by that. Is when you take M minus its average on a ball of radius R, your averages on a ball of radius R, this has to tend to 0 when R goes to 0. Okay. So that's already quite nice, right? That you have this type of properties for this vector field M that is not BD at all. This already looks a lot like a map. But what we would really like to know is, okay, let me call them A prime and B prime. A prime would be nu equal to 0. And B prime would be that you have Lebesgue points. So for points outside the jump set, do you have that actually you can replace this average on VR at scale R by just one single value that does not depend on R. You think of it as the value of M at the point X. Okay, so this is open. That first thing, let me just say that I don't know how to do it, but there has been some quite recent progress by Elio, where he shows that this nu, maybe it's not 0, but it has really a very, very specific shape. So that what remains to do is really to analyze some very particular types of configurations. But I'm not going to talk more about that. I'm going to be more interested in that second property. I mean, can we show that those points, which in principle have just have vanishing mean oscillations, they are in fact Lebesgue points? This is really the focus of this talk. And okay, let me just say that one traditional way to prove that a VMO point is a Lebesgue point is this Campanato type of iteration that tells you that, okay, it goes to 0, but if you know that it goes to 0 with an algebraic decay rate, then you actually have a Lebesgue point. So this is really the point of view we're going to adopt here. And let me state the theorem that we prove. So we cannot prove B prime. We have to restrict a little bit the set of points X that we consider. And still we get that if you look at omega and you look at the complement of Lebesgue points of M, and I write love here, I mean the set of Lebesgue points of M. At least it has dimension less than 1. And here by dimension I mean the Hausdorff dimension, so I can rewrite this as saying that if you take a Hausdorff measure of dimension a little bit more than 1, then this has to be 0 for that measure. Okay, this is just a rephrasing of that statement. All right. Okay, so in the remaining time, I hope I will be able to explain a little bit how we prove that type of things. And first, let me mention that it's proving this type of thing. This is very much inspired by previous results on Berger's equation and more generally scalar conservation laws, maybe of more dimensions. Burgers u plus dx equals 0. Scalar conservation will be maybe higher dimensional, but of the same form. So for these types of equation, you can also define what entropies are. Really with the same type of idea that if you apply the chain rule and you have a smooth solution, then you get something at 0. And okay. For Burger, the equivalent of that theorem, we proved it with Felix Otto when I was doing my postdoc in Leipzig. But this was really a two-dimensional argument relying on the idea of compensated compactness. And that's and then Elio, he method of putting that type of things that would apply also in higher dimensions. Okay. And I will try also to explain to you why the type of things that you can do there, you really need something new when you are in that setting for the eikonal equation. So I hope at the end you will at least be convinced of that. All right. So now let's.
Sorry. So just on this. So does it mean that what's away from Lebesgue it's also rectifiable, but you don't know if
no, we don't know that it's rectifiable. What I'm going to do next is be a little bit more precise about that statement and compare a little bit the sets of points that we know are Lebesgue with the complement of that jump set that appears here. And you'll see that, I mean, the points we are missing, basically. Mm-hmm. And to do that, I need to find some objects. The first object is a measure that encodes all my entropy productions. And this is just going to be the supremum measure over all possible entropies that have a bound on their second derivative. Of this thing. So, okay, what is that object? These things, they are positive measures, non-negative measures. And basically, this time this is a supremum, but this is not really a pointwise supremum. This means it's the lowest positive measure that is above all this. This is an object you can define, you can characterize with formulas, etc. And for the purpose of this talk, I'm really gonna think of this object as some kind of where, so when you take nu of some set, I think of it as the energy contained in that set. And once you define this, you can give a formula for that set, that jump set Jm, that appears in the result of the Lellis and Otto. Or rather, I'm going to define it by complement. It's basically, so the complements, the points that are not jump points, they're basically all points where that measure looks higher than one dimensional, which can be expressed simply like that. You look at the measure of the balls of radius r, you divide by r, which would be roughly the measure if it was a one-dimensional measure, and you want it to go to 0. So those are, I mean, morally speaking, those are the points where you don't expect to have one-dimensional jumps. And instead, we cannot. So what we would like to show is that all points that have these properties, this property and our VMO, they are in fact Lebesgue points. And we cannot really show that. And here, you recall my remark about the Campanato type arguments. What we need to do is we need to ask for some quantitative decay of that quantity. So basically, if you know that this goes to 0, but with some rate, okay, alpha, or some alpha strictly positive, can be as small as we want, but it has to be there. and you know that you have a VMO point, then in fact, you have a Lebesgue point. Now notice that here I get rid of X. So the point I'm looking at is 0. I mean, chose my coordinates so that everything is centered. So this is, in fact, this is really our result. And once you have something like that, just with the covering arguments, you know directly that the points that are not Lebesgue, they must have H1 plus say alpha over 2 dimensional measure is 0. And so you see that in principle, we may be missing a bunch of points where this thing decays, but maybe logarithmically. So I don't know, maybe it answers your question, right? Okay. So I have maybe like 20, 25 minutes to tell you a little bit about the proof of that statement. So the proof basically combines the ideas of Elio in that paper where he did with conservation laws, and a new ingredient that you have to include when you're looking at the eikonal equation instead of conservation. So I'm going to try to explain basically this argument and why you really need to do something new when you're looking at the conservation law at the eikonal equation. So first, I'm going to define a few further things. So basically, you want to look in some sense at oscillation at scale r in an integral sense and show that they decay algebraically, right? And here we are going to measure those oscillations by quantity here, I call h of r, which is the supremum over all points that are in a ball of radius 2r of averages of m on balls of radius r centered at those points. The picture you want to have in mind is you have this ball of radius 2r, and you're looking at averages on balls of radius r here. Okay, I'm looking at the maximum difference you can obtain when you do these averages here. So it's kind of reasonable when you think of this campanato business to expect that if you're able to show that this quantity decays algebraically with R, then you have a Lebesgue point. And so this is really what we do. If you assume that this decays algebraically and you have a VMO point, then in fact, we show that this H of R also decays algebraically, maybe not with the same power, but it also decays algebraically. And I mean, once you have that, then it implies that you have a Lebesgue point by this campanato iteration argument. Okay, so from now on, what I'm going to concentrate on is how we prove that equation. And okay, realize.
So how is beta? You said 12.
I don't remember exactly. I mean, we can give it explicitly. It's smaller. It's smaller. Yeah. Maybe in the Hausdorff. I don't think I will give the exact constants in my sketch of proof. It's something like alpha over, I don't know, 20 plus 2 alpha. Or something. Yes. Yeah, we use something else. So this is definitely not optimal what we do, and we don't try to optimize it. And in some sense, I mean, even if you can take alpha here, you still cannot say something better about the Lebesgue points because you really need that algebraic decay to. This is something we really don't know how to go beyond. So this implication star, it relies on proving the dichotomy, which is the following. So basically, okay, when you look at this, what you would like to say is that the oscillations, they are controlled by the energy, and if you know how to show that, then you're in good shape. But if this is the case algebraically, then this is. But see, I mean, I insisted here that I'm really using the fact that also I know my point is VMO, and this is going to be related to the second part of the dichotomy. So oscillations are either or controlled by the energy, and this is going to be one of my dichotomy, or they are in fact so wide that they contradict the VMO assumption. And let me be a little bit more precise about this dichotomy. So controlled by the energy, what I mean is, here I will have to take a slightly larger ball, or in fact quite larger ball, but the radius large r is going to be still proportional to small r. And the energy in that larger ball controls the oscillations in that smaller ball. And here, let me tell you what R is. It's basically R over H squared. So there is actually a constant here. I'm not going to show you all details. One. Okay, so this gamma is some positive number that we know explicitly. I think it's 11, but I won't. You won't see why exactly. And okay, if you have that kind of estimate, then you do the algebra of using the fact that this is less than large R to some power alpha, and then you put H on one side, small r on the other side, and you realize that you really do get that type of decay. And what is the other side of the dichotomy? That whichever direction I look at in my circle, I look at the proportion of points in my ball BR which are sent by M a little bit away from that point. And this proportion is a fixed universal quantity. So basically, any point I look at, I know that I have a lot of points that are sent well away from it by M. And this is contradicting the VMO thing. So let me write down what I just said. You look at the measure of BR intersected with the set of points where M is at a fixed distance from the direction. Okay, and this I claim it's larger than some universal constant times r squared. Okay, and because this is true for any z, any direction z, you get a contradiction with the VMO assumption, because the VMO assumption tells you that at scale r, you should have, most of the points that are very close to some fixed value in the circle that is given by the average there. So basically, that's how it goes. Because you assume that you are at the VMO point, this in fact cannot happen. And so you are in that setting, and so you have that implication.
I'm sorry, what's the distance? What the length of the one collision thing? R, you said?
So this is, this one?
Yeah.
This is some universal constant. Maybe it's 1/10 or something like that.
Okay.
This thing here and this constant here are just absolute.
Okay, great. But you fix that thing, so it's independent in R.
It's independent of R. Yeah. Yeah, that's probably. pi over 20, like that. And we don't try to optimize any. I don't know how clear that picture is. I mean, really, I want M to be sent to this red set away from it. So before I give a little bit more details about the proof of the dichotomy, I promised that I would explain what is different from the Burger or conservation laws setting. And in fact, in the setting of conservation laws, you just have the first option. You don't have a dichotomy. You don't need to consider this. And it's very easy to understand why. It's because of that vortex solution that I showed you in the beginning. Why do you need this? Well, you just look at your solution here. You can use the formula. This would be just the radial field that you rotate by pi over 2. It just happens that this solution, it has 0 energy. Okay. So nu is equal to 0 for that solution. But obviously, if you look at averages on small ball, the average of M is always 0. So this this quantity H is always over the 1. Whatever. Okay, so there is no way you're going to fulfill H with the energy. Right? But you can see also that you are in the second point of the dichotomy, right? Because here you get closer and closer, and really looks in all directions. It has really a non-trivial proportion of points that are sent to any direction on the circle.
That's not a VMO.
And exactly, I mean, that point in the center is not a VM. I mean, for the same reason that this H is over the 1, I mean, you look at the integral of M minus its average, because the average of 0 and M is of modulus 1, this is over the 1. Okay, and these types of solutions, they are not present in the Burger setting, so you really need to, to work with them when you put that type of results. All right.
But does it mean that you can have only these vortex points in the Y solution?
So I think that's the only example I have, but maybe Benoit has another example. But we don't know that. I mean, we cannot say, okay, those are the only points that are that are not VM. I mean, we have not thought of putting something like that, but I don't think we can. Okay, so in order to tell you about the proof, I have to introduce new tools, new definitions. And the main tool here, that story, is a kinetic formulation for entropy solutions. Kinetic formulation is something that people have known for a long time in the setting of scalar conservation laws. And in that setup of Aviles-Giga and the eikonal equation, it was noticed by Java and Berta in a paper, I guess, probably around 2000. Okay, what is that combination? Call it K. And this is something that where you add a variable S on the circle. You look at points X which are sent to an M with positive scalar product with that point of the circle. And the kinetic formulation tells you something about the transport of this set of points in that direction here. And it tells you that it's not too wild in the sense that it's equal to the derivative in S of some measure, sigma. So here, X is omega, and S is a new kinetic variable that we introduced that is in the circle. So I identify a periodic real line with the circle here.
So when you do that, actually, proving that it's actually Holder continuous at that point as well, or your estimate doesn't imply Holder continuous?
I don't think it does. It would if we would really be estimating the regional oscillation. I think with that definition, when you go through the proof, you're not really proving it. Okay, I'm not sure. Probably you do.
You actually are estimating the mean oscillation. I mean, this implies.
I think that should work.
It did imply a mean oscillation of that order.
No, in fact, because when we use so it would imply Holder continuity if I also know that the Villemot property, the second part on the left of my application, it also had like algebraic decay, but then it's trivial. So
no, but I mean you need the exponent to be the same on the whole ball.
Yeah, but
Campanato spaces.
It's locally Holder, right? At every point we have a Holder exponent.
Yeah,
It's proof continuity, right?
Yeah, but you need the same exponent to have a Campanato spaces and embedding into Holder. You have to pay attention to the exponent.
I mean, you can look at all points that give you one specific exponent, and although that set may not be open, still you are held on that set. But I mean, since it's not open, it's not really
it doesn't
telling you that much, right? I think it does. Okay, I'm going to go through the details of that last implication that is in parentheses. In principle, it should be like that. But again, I mean, Holder continuous on a set that is not open. What can you really do with that?
The continent doesn't see open or closed.
No, yeah, and that's why you can still talk about this, but still.
Like all your Lebesgue point are a point of continuity.
In some sense, yeah. Okay, so back to the kinetic formulation. Okay, so right now this is just an equation. Let me try and tell you a little bit what its relationship with the assumption that we have that the entropy productions are measured and what kind of properties it implies. So by the way, here we want to recover the energy. It can be expressed, but that thing I call nu. It's just projecting this measure sigma into the x component. Or equivalently, we think of sigma, you integrate it with respect to the s. And okay, maybe there are some constants here, but basically that's the sigma is basically the energy once you integrate it overall over the kinetic variable. And okay, what does that thing have to do with the eikonal equation and with the entropy production? Well, it's quite easy to say, to see. First, integrate this thing with respect to S. Well, what comes out of it is the divergence-free condition. Basically, when you integrate with respect to S, this goes away because this was the derivative of someone, and this gives you m of x, have to be constant. Now you can keep playing that game and integrate against other test functions. And when you do that, this will not go away anymore. You will have some measure, but here we'll get some entropy production. Okay, so this is really the relationship of that equation with the assumptions that we made. So that's one point, which still does not give you much intuition about how to understand that type of equation, and maybe to understand it, it's a good idea to look at the case when you have no right-hand side. That's 0. Yeah. Just to give us a little bit more intuition. So when you have 0 energy, we just provide that equation. Okay, so you are basically saying that this set of points, the set of point X, for which M loops in the direction of E to the IS, this set of points is freely transported by that direction. By the way, this was used a lot by Xavier, Otto, and Bertam, again around 2000, to really characterize the solutions of that particular equation with 0 energy. But okay, let's just make a picture to to understand what it's telling us. So you have a point X. You have here your vector M of X in the direction. Now you're looking at all S's that are in that set. The half circle of all vectors that have positive scalar product with M. Okay, so here maybe I can be looking at the vector here e to the IS, right? It belongs, I mean, it gives you a value 1 in that characteristic function. And now on this one, I'm looking at the transport in that direction, right? Okay, why not? And what that equation is telling me is that now I look at a further point along that line, where the vector M, it has to have positive scalar product with that vector. Right? So you know that M at that point, say Y, M of Y has to belong to that half circle. Okay, so this is what this 0 energy equation is telling you. And this is really the type of pictures that you want to have in mind to understand our proof of the dichotomy there. And okay, maybe one thing to say is that basically if you play with all the directions here, what comes out of using this type of picture is that M is constant along characteristics, which is, okay, and I put quotation marks because this is not true. There are some almost everywhere statements here, etc. But the characteristics are the lines orthogonal to M, so basically you know that along line orthogonal to M. And in fact, it's not true. It may happen something like that, which is exactly what happens at the center of the vortex, by the way. Okay, now I see that I was very ambitious with what I wanted to tell you. Because I think I have to stop. Yeah. So? No? Yeah. So, yeah, 5 minutes? Okay, cool. Maybe it will give me enough time to explain the first step of that dichotomy, which is basically obtaining a weaker dichotomy. And it's good. First step is you use some type of linear argument to transform okay, the fact that you know that that quantity positive. So I have points x1, x2, which are in the border radius 2r. I have my quantity h, which is the difference between those two averages, and I think of it as big as possible. And the first one is some type of Riemann argument that says that if that thing is big, basically I can say something about sets like that for some specific values of S and S. So okay, I have my two balls here, and I know that the averages they differ by h. Then I look at the proportion of points that are sent to that. Right? Now here in that thing, I look at the proportion of points that are sent to a half circle that is kind of opposite. Okay. And okay, here the proportion of points that do that, I call it say rho 1. Here the proportion, I call it rho 2. So this is the proportion of points in that small ball of radius r that are sent by m to that semicircle. And what I can say by a Fubini argument is that I can choose a direction S such that that proportion, when I sum the two, I get something that is strictly larger than 1. And how strictly larger than 1? By this factor of h. Okay. So I mean, you can imagine this is kind of a pain to write, like all the right integrals, but you can imagine that something like that should be true. Basically, I'm just saying that because they have very different averages, I mean, I have to be able to find more than half the points here that point in some direction, and more than half the points here that point in the opposite direction. Okay. Then the second thing is, okay, imagine what would happen in that situation if mu was 0. This is where we get all our intuition from. And okay, so I have my ball here, I have my points here. And this thing, okay. So here I already lied to you a little bit. In fact, you can also play a little bit by that direction, and you're allowed to those two directions that I get, you're allowed to rotate them a little bit. And you still have that property uniformly in whatever rotation, very small rotation here and here for those two corresponding proportions. And you play that game with something that is like that. And here, by the way, the angle is the order h squared. And here you play that game here. Here you play that game with also rotated by h squared, but in another direction. Okay. So you know that you have more than half the points here that go here, more than half the points here that go here. And now you can have this direction here and this direction here that have a positive scalar product with m in that region. So what you do is this direction, this one here. And since the proportion of points here in this region and in this region, the sum of them was larger than 1, you will get like a little bit of points that lie in the intersections of those things. And here you have like a proportion of order h, which are sent to basically, I mean, you have to keep positive scalar product with, I mean, you have to lie in that semicircle and also in that one. You see that you actually have to lie here, the intersection of those two semicircles, because this set, they have to be freely transparent. Okay. And And okay, what you want to know is also how far you had to go there. But basically here, because you're allowed to, the lines, they are allowed to turn by h squared. This distance r is like r over h squared. So this is where that thing came from in the dichotomy. And now what I'm not going to have time to explain is that you want to make this quantitative. Okay, no, first, sorry. I'm going to stop soon. Okay, you play this game with this, you get that the proportion of points which are going in that direction is basically larger than h than r squared, more r squared. Okay. But you could also play that game rotating the things in the other directions. Then you would go this way, and you would get the same thing in a completely different region of my ball, the R, but in exactly the opposite direction. Okay, it's just by rotating my things in the other direction. And you also get that. So you see that now, I mean, you have something that looks a little bit like my second point of the dichotomy, except the proportion of points that are looking in very different directions, they are not, it's not an absolute constant. It's something that is h, which can be very small. So we have not won yet, but somehow this is the first step. And then the second step is to transform that type of information into something much stronger that gives you the second point of the dichotomy. And also what I did here is that you want to use the general kinetic formulation with a non-zero right-hand side to actually make this quantitative. So the statement is, if the energy is small enough with respect to h, then you really do have that. Okay. And so you have the dichotomy, either the energy was much larger than h to some power, or it is very small. And I'm going to stop here, I guess.